In this particular problem, it's just there's a large container that is filled with some sort of liquid, which has a density of 1.1 times 10 to the third kilograms per meters cube. And it says there's a small hole of area 2.5 times 10 to the negative 6 meters square to the side of the container that is a height below the low water level. And then it says at the same time, liquid is also added to the container at an appropriate rate of, at an appropriate rate so that H remains constant. So the height here stays constant. So essentially there's water coming out. There's water coming out, and then there's water being poured in so that the water level surface essentially stays constant. And it says here the amount of liquid collected in the beaker in 2 minutes is 7.2 times 10 to the negative 4 meters cubed. Okay. All right. So the amount of water coming in is the same as the amount of water coming out in order for H to stay constant. So if you need to, pause, read A, B, C, and D. All right, let's go ahead and do A and B. Let's do a quick run through this. Part A asks us to calculate the flow rate from the hole in units of meters cubed per second. So based on the information given, I am given the volume of the water that's collected here, and I'm given the time, which is 2 minutes. So I know volume, I know time. So to do part A quickly, I know that flow rate is volume over time. I know the volume, I know the time. Time is 2 minutes, volume is 7.2 times 10 to the negative 4 meters cubed. So I'm just going to plug and chug. So in the numerator here, which is the volume, which is 7.2 times 10 to the negative 4 meters cubed, because that's how much water is being poured in. It's also how much water is coming out, which is collected. In the denominator, time is 2 minutes, but I do want to point out this is 2 minutes. The unit that it wants is meters cubed per second. So all you have to do is recognize that this is 2 minutes, so convert 2 minutes to seconds. So for every minute, there are 60 seconds. So therefore, 2 minutes would be equal to 120 seconds. That's just a basic conversion there. Hopefully you didn't get lost. On that, simplify your work. And if you do the numerator divided by 120 seconds, you'll get that Q, volume rate, is 6.0 times 10 to the negative 6 meters cubed per second, which is the unit that it wants. And we are done with part A. Part B wants us to find the speed as it exits the little hole here on the side of the container. Well, the quickest way to do this one is to set up your flow rate, which is to go to area times speed. I already know flow rate because I already found it. Q I just found as 6.0 times 10 to the negative 6 in part A. I know the area. The area here is given as 2.5 times 10 to the negative 6 meters square. So really to find V, I need to first go ahead and algebraically manipulate the function by dividing both sides by A. So I can say V is simply equal Q divided by A. Well, I know what Q is, I know what A is, so it's just plug and chug. A here is 2.5 times 10 to the negative 6 meters squared, which is given. Q, once again, I already found in part A. So Q is 6.0 times 10 to the negative 6 meters cubed, though, per second, because that's the unit that I wanted. And then divided by 2.5 times 10 to the negative 6 meters squared. Once again, pay attention to units. Cube is volume, square is area. So therefore, if you look at this term correctly, there's 10 to the negative 6 in the numerator, there's 10 to the negative 6 in the denominator. I'm just going to go ahead and cross it out just so my calculator works less. So really at the end of the day, to find the speed that it shoots out at this little hole, all you have to do is 6 divided by 2.5, which you'll get 2.4 meters per second. So that's the speed. All right, that is it for A and B. Let's do C and D. It says calculate the height needed to cause the speed to shoot out at 2.4, as we found in part B. So I'm just going to set up Bernoulli's equation here. The atmospheric pressure on the top is 1 atm. The pressure outside the speaker in the same environment is also the same, which is also 1 atm. So I'm just going to label it for you and then cancel it out. So P1 here is 1 atm. P2 is also 1 atm. So I'm just going to cancel that out in Bernoulli's equation. And then last but not least, not last but not least, almost last. V to start, V1 at the top of the beaker is 0. So I'm just going to go ahead and cancel that term out. And that water level remains constant anyway because it's saying water is being poured in. Okay. Here on the right side, I cancel out the rho GH2 because I want to take the lowest point where the hole is to be my lowest point, because that's essentially how much water would drop. Okay, so it's important as you do these practice problems, define a reference point where it's 0. So I'm going to say where the water exits the container, that is the lowest point. Therefore, because it is the lowest point, H2 would be 0. So therefore, rho GH, H being 0, which is give you 0. So on the left side, all I have left here is just rho GH1, and that on the right side, all I have left is 1/2 rho V2 square. But as you can see, rho appears on both sides, so I'm going to cancel that out. Now, part C though asks us to find the height of the liquid, right? So H1. Well, to find H, I need to get rid of G. So to get rid of G, I would just divide both sides by G. So on the right side, V2 square is in the numerator, the 2 is in the denominator, and I want to combine G with the 2 because when you move the G to the bottom right, it goes in the denominator, or you can say divide both sides by G, however you want to do your algebra. So really, to find H1, I need the speed at the exit junction where the hole is, which we already found, which is to be 2.4. I want to square that, and divided by 2g. G is the acceleration due to gravity at the surface of the planet. Okay. All right. So I'm gonna plug and chuck here. So v once again is 2.4. Don't forget the square, and 2 gets carried down. G is 9.8. So really, ultimately, the height here is going to be 0.294 meters. That's it for part C. Now part D says, it says now suppose that there's now less liquid in the container, so H is reduced to H2, right? Now, well, Bernoulli's function states that the exit speed depends on the height of the water. Well, as the height decreases, the water will eventually shoot out slower because, you know, this function here, watch where I'm circling, right? V depends on H. Well, if H goes down, V also has to go down, okay? So therefore, I'm just going to go ahead and say that it's going to move to the left of this beaker because, well, if it shoots out slower, it doesn't cover as much horizontal distance, right? So here's the proof for it. Well, how do I know that it moves to the left? Well, in order to find delta x here in this diagram, we can use kinematics. The change in the horizontal position or the horizontal displacement here is just the velocity that it shoots out at, aka the x direction times the time. Well, I know once again from this function here that v will go down because it depends on h. So if h goes down to half, v will decrease this. How much, I don't really care because the question here is not saying a ratio, it's just saying where would it land. So I'm going to say to the left because v goes down. So according to this function that I just put up on the screen here, x is equal to vx times t, but vx is height dependent. So vx, if you solve this function, that's boxed in red to the left side. So to solve for v, multiply both sides by 2 and then square root it, and that's where the square root 2gh comes from. I highlighted h here because, as you can see, x depends on this quantity, right, in parentheses. So if h goes down, everything underneath the radical also goes down. Well, the square root of a smaller number will give you a smaller answer because t in this case stays constant because the height that where the hole is stays constant. So the time that it takes to reach the ground will be the same regardless of how fast it shoots out. Okay, because t depends on height, and the height here in this case is d, and lowercase d here stays the same. So times the same, h goes down, this parentheses goes down, therefore x also goes down. And that would be my justification. So if h goes down, x goes down. Alright, I hope that helps. Stay nerdy, don't be whack.